The Earth is a powerful place, constantly changing through slow geologic processes and sudden dramatic events we call natural hazards. Think of an earthquake, a flood, or a hurricane. These events are part of the planet's natural systems. They only become a hazard, a threat, when they intersect with human communities, putting our lives and the things we build at risk. Our goal is to understand them well enough to minimize that risk. When we study natural hazards, the most important thing we can do is ask questions. Questions drive scientific investigation. By asking, "How often does this happen?" or "What warning signs exist?" we unlock the knowledge needed to prepare. Science focuses on accurate forecasting, predicting the event, and engineering focuses on mitigation, reducing the damage. Together, they help us protect people and property. Let's start with a big question about earthquakes. Are they sudden, or can we see them coming? The unfortunate scientific fact is that most significant earthquakes hit suddenly, without any reliable short-term warning. We can predict where they will happen, along fault lines, but not when. Because of this, we can't rely on a forecast. Instead, all our efforts must go into preparedness and building strong enough structures to survive the shaking. Since we can't reliably forecast earthquakes, our technology is focused on mitigation. Engineers have developed design solutions like base isolation. Think of giant shock absorbers installed beneath large buildings to lessen the seismic impact. On the human side, the solution is simple but critical, practicing drop, cover, and hold-on drills. This human action, backed by engineering, is the best defense against a sudden quake. Now let's ask a question about hurricanes. What allows scientists to reliably predict them? Unlike earthquakes, hurricanes give us significant clues. The scientific principle of heat transfer tells us that hurricanes need warm ocean water and specific wind patterns to form and grow. We use satellite systems to constantly monitor these conditions, which allows us to forecast a storm's path and intensity days in advance. The technology for hurricane preparedness centers on those reliable forecasts. Scientists use complex computer models to predict where the storm will make landfall. This data then drives human actions, like issuing evacuation orders. We also have engineering solutions, like constructing massive, movable storm surge barriers in coastal cities, which apply physical principles to block the wall of water pushed ashore by the storm. Next, let's ask about volcanoes. What specific signs can we monitor to predict an eruption? Volcanic eruptions are much more predictable than earthquakes. The principle of pressure buildup tells us what to look for. Scientists place sensitive tools like tilt meters and GPS on the volcano's slopes to measure when the ground starts swelling. They also measure increased steam and gas emissions. When these signs increase, it's a reliable forecast that an eruption is likely. Volcanic preparedness uses this advance warning time effectively. Scientists create hazard maps that show communities where lava flows and dangerous mudslides, called lahars, are most likely to travel. The primary human preparedness is practicing evacuation routes. Because the scientific monitoring gives us days or weeks of warning, communities can implement an orderly and safe retreat from the danger zone. Let's look at a fast-moving hazard: tornadoes. What conditions must be present for a tornado to form? Tornadoes are born out of severe thunderstorms when the air is unstable and wind speeds change with height, creating a spinning effect. They form and dissipate very quickly. Scientists rely on Doppler radar, a technology that sends out waves and measures the return signal, allowing them to detect rotation inside a storm cloud. Tornado preparedness relies on speed. Since the warning time is often just minutes, the technological solution focuses on rapid warning delivery. Sirens and emergency phone alerts are key. Our engineering solution for mitigation is creating reinforced shelter, building basements or specially designed safe rooms in homes to protect people immediately upon receiving that short notice. Thinking about water, we ask, how do rainfall and ground saturation affect flood likelihood? The scientific principle here is that the ground can only absorb so much water. Once the soil is fully saturated, any additional rain immediately turns into surface runoff. Scientists monitor river levels with stream gauges and ground wetness with soil moisture sensors to forecast the likelihood of a flood before the rain even starts falling. Flood mitigation technology is all about controlling the flow of water. Engineers design and build large systems like reservoirs, giant holding ponds, and levees, raised embankments, to contain or redirect floodwaters away from communities. On the individual level, human preparedness involves simple engineering, like building homes with elevated foundations, and social actions, like purchasing flood insurance to minimize financial risk. It's important to ask how our actions influence hazards. How can human development increase a hazard's impact? By ignoring science and building our communities directly on natural floodplains or vulnerable coastlines, we massively increase the effect, the financial and human cost of a flood or hurricane. Mitigation involves using scientific data to inform smarter zoning laws and urban planning, essentially choosing not to build in dangerous areas. Whenever we implement a mitigation technology, we must ask, how can we use evidence to evaluate if it actually worked? The answer is through data. If a town invests millions in a new levee system, scientists must collect data on the next major storm. They compare the number of homes damaged or lives lost in the protected area versus an unprotected area nearby. If the data shows lives and property were saved, the design solution was effective. The warning time is not the same for every hazard. We ask, do all natural hazards offer the same amount of warning time? Absolutely not. Long-term hazards, like rising sea levels due to climate change, give us years or decades to plan. Hurricanes give us days. But for a sudden earthquake or a developing tornado, the warning is incredibly short, seconds or minutes. This difference dictates how we focus our preparedness resources. For global hazards, we rely on technology that can see the whole Earth. How do satellites help us monitor hazards globally? Satellites provide a consistent, continuous stream of data on large systems. They measure ocean surface temperatures, track the movement of massive cloud systems, and even monitor ground elevation changes on volcanoes. This global view is critical for early warning systems that protect multiple countries. Scientists don't just look forward, they look back. We ask, how do scientists use data from past events to predict future events? They analyze historical records to determine the frequency, how often, and magnitude, how strong, of past events. This data allows them to create probability maps, like risk zones for earthquakes, which we use to inform strict building codes and community evacuation plans. Sometimes, one monitoring system helps with a completely different hazard. High-tech technology developed for an earthquake helped predict a tsunami. A major underwater earthquake causes a sudden change in the seabed. Deep-sea sensors detect this change immediately. This data is transmitted rapidly, allowing scientists to issue tsunami warnings to coastlines thousands of miles away, giving people crucial hours to reach high ground. It's important to ask a social question. Do all communities have equal access to hazard preparedness technologies? Sadly, no. Reinforced homes, reliable sirens, and even quality hazard insurance are often more accessible to wealthier communities. Our scientific and engineering efforts must also address social equity to ensure that warning systems and mitigation plans are effective and accessible for all people. This process is a never-ending cycle of protection. We start by monitoring the Earth, which leads to a forecast of the hazard. That forecast drives the development of design solutions, like levees or warning apps. Finally, We evaluate the results to see what worked and what didn't. By continuously asking questions and using scientific knowledge, we can make our communities safer and less vulnerable to the unpredictable power of nature.